Hello, my name is Jared Harrington, and this is my Lab 3 black hole. For this lab, I'll go over the table of contents. I'll begin with an introduction, then I'll move on to explaining the fundamental physics principles that apply in this lab. Then I will move on to part 1, which will have the computational code and the results. Then I'll move on to part 2, which has the computational code, and then show the results of part 2. Then explain any sources of error I got, and then the questions at the end. So the purpose of this lab was to determine the mass of a black hole by analyzing a star's orbit using GlowScript. Then utilize the mass of a black hole to find the required initial velocity needed for a ship to fly around the black hole without crashing. The fundamental principles in this lab were Newton's second law, Newton's universal law of gravitation, and then parallel and perpendicular forces. Here I have an introduction of the experiment results. For part 1, the system was a star and the surroundings were the black hole in space. The mass of the black hole was determined to be 1.23 e to the 34th power kilograms. And then for part 2, the system was the ship and the surroundings were the black hole in space. And then I have the initial velocity shown right here. So some important physics principles in this lab were Newton's second law, and the equation shows the momentum principle, so the change over momentum divided by the change over time. And then we have Newton's universal law of gravitation, and that's shown right here. And then for the parallel and perpendicular forces, you would set both of them equal to the net force and then apply the momentum principle to them. And then the parallel force in this case would be the changes in speed, and then the perpendicular force would be the changes in direction for this slab. So for this, now I have the computational code. So to begin, I have the initial and final velocities, and then I use the momentum principle to get the initial momentum and the final momentum, and then I calculated dp dt, found the net force, and then this section is the parallel components, and this section is the perpendicular components. And then here are the initial conditions. For delta t, this is equal to 1 Earth day, so 24 hours times 60 minutes times 60 seconds. And then the gravitational constant and the mass of the star were both given. And then here are the components that I found. So for the first line, I was able to calculate R, and then the second line, I calculated R hat, and then the third line, this is the gravitational force, and then that repeats. And in this line, you're just adding the two gravitational forces together. Here you have the distance from the ship to the black hole, and then here's the velocity update formula, and then down here I use the position update formula, and then here are the initial conditions. So for the results of part 2, as I said earlier, here's the velocity. It was done or calculated through guess and check. So there could be inaccuracies, and then the closest distance, there also could be inaccuracies with this too. Some sources of error I could have obtained would be for part 1, I could have used a lengthier period to gather more values in order to ensure a more accurate mass for the black hole. And then for part 2, when I averaged the mass, the value given was rounded, meaning it was not as accurate as it could have been. And then the initial velocity was found through guess and check, which could have created inaccuracies. So for what does this mean? Discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So the answer is for net forces, you must know each individual force adding on the system and sum them up. Whereas in the rate of change of momentum, one only has to account for the change of velocity and motion in a system. And then for the what if question, what initial velocity would your spaceship need in order to enter into some kind of orbit around the black hole? And then this is the value I got. I got this through guess and check, so there could have been a better answer, but this is the closest I got.